We defer questions to the afterwards. I can take this. Thanks a lot for this. And now, last but not least, we have Mario BERTAINA, with whom I had the pleasure to work for many, many years, and he will talk about ultra-energy cosmic rays.
Thank you, Marco. It was really a mutual pleasure to work with you, to fight scientifically with you many times. And first of all, I would like really to thank this place, the embassy, that I had the honor and the pleasure to visit. I was discussing with some colleagues before since more than 20 years. I was postdoc at RIKEN, which is my second house, basically. My first house in Japan, and I had the pleasure to come here and to discuss the possible progress of the JEM-EUSO program with the scientific attaché, so Angelo Volpi, Alberto Mengoni, Enrico Traversa, and the current scientific attaché, Gianluigi Seriani, that I had the pleasure to meet a few months ago. So I really would like to thank, on behalf of also the Italian group, the support and help of this embassy all along the years for all the development that we have done with our mission. Thanks to all the JEM-EUSO collaboration, what I'm going to show is due to the support and contribution of many countries, about 20 countries probably joined during all the history of EUSO and JEM-EUSO collaboration, and the key players are here. And thanks to some of you, I have stolen some of your slides in your presentations, conferences. You're much more skilled than me, and so I use them. And I will insist today more on the contribution between Italy and Japan, as this is the nature of our meeting today. And I have put a lot of videos to keep you awake, because this is the last talk of today. I hope it will work. Let's see. So these are most of the effort that we have done with this JEM-EUSO program. You can see missions from ground, like EUSO-TA, from stratospheric balloon, EUSO balloon, EUSO SPB-1, SPB-2, and mini-EUSO on the International Space Station. As was already mentioned this morning for the JEM-EUSO meeting, JEM-EUSO and EUSO were born here in Japan with Italian contribution. You see here Professor Livio Scarsi and Osvaldo Catalano in the office of Toshibi Suzaki at RIKEN, discussing the start of the EUSO project, and a few years later, the kickoff meeting of JEM-EUSO here in RIKEN. Some of you will recognize yourself in these pictures. We have also organized several workshops, also with the help of the embassy here, also to think about the science, our scientific case, and also we have published our results on international peer-reviewed journals. So these are some pictures of our meetings in Italy and in the RIKEN that were organized along the years of the project. We have to thank the Italian Ministry of Foreign Affairs for the long support that we have received. Our project JEM-EUSO was considered a project of grand relevance in space science in collaboration between Italy and Japan, and you see all the different projects that have been funded by this project. And the partners of this project are listed here: universities, INFN, and also INAF from the Italian side, and different space companies, or in general companies that helped us with their support to build up our instrumentation. And similarly for Japan, with RIKEN, Saitama University, University of Tokyo, Konan University, and also the Japanese companies. We were received also funds from different national institutions, like the Italian Space Agency, INAF, INFN, and the Italian Ministry of University and Research along the years, and similarly for Japan. And with that, we had the opportunity to organize many meetings and also improve their scientific knowledge coming to Japan and so on. So let's start with a bit of science. Okay, so the first video works. So I thought to put also some videos for those which are not expert in cosmic ray science. So what well, of course, there were already the talks before, but I'm focusing on ultra-high energy cosmic rays. These are potential sources like active galactic nuclei, black holes, that at the center of galaxies are collecting matter, and there are accretion disks and explosion that give cosmic rays sent to the intergalactic magnetic field, and they travel, they are deflected, the magnetic field, and at the end they reach also our galaxy, the solar system, and some of them are impinging on the Earth at the top of the atmosphere, producing the ultra-high energy cosmic ray cascades that we wanted to measure with our space experiment. Here, this video is made by NFM for the JEM-EUSO experiment, which is the largest one on the Earth in Argentina, 3,000 square kilometers, to detect these events, which are just probably 1 per square kilometer per century. And of course, we would like to live a century, but it's better to detect them by having very large areas capable of collecting them. So you see, this is already an ambitious program from Earth. It's very hard to go larger in dimension. Space gives us an opportunity. And the intriguing things that we are working on are these ultra-high energy cosmic ray. The highest energetic events reach 50 joule, so macroscopic energy. A single proton might have this energy. So in terms of macroscopic energy, it's not that much. I mean, you know, Italy is now the best country for tennis, so I put Italian tennis players. So the speed of the tennis ball of these players is comparable to order of 50 joule or so, but in a tennis ball there are 10 to 19 times protons, so the energy of the ones that we are looking at are 10 billions of billions more energetic of what are the protons and the neutrons of the tennis ball shot by this player. And if we would like to use our current technology at CERN to try to accelerate this particle at these energies, we should have an accelerator with this technology as big as the orbit of Mercury. So this is not possible, and that's why we would like to look for the events coming from space, which are generated by, as I said, black holes, pulsars, and so on. And the advantage for those which are, of extreme energies are the fact that hopefully, no, okay, they don't go well, but if at 10 to the 20 electron volt, they might, if they are protons, go straight, and we can point directly to the sources which are producing them. With our technology and our science, we would like to study the universe at different level. We were mentioning before the cosmic microwave background, the protons at these energies interact with the CMB, so we can also measure the effect of this interaction with the CMB. When these cosmic rays interact in the atmosphere, they do nuclear interaction, so we can study fundamental physics, particle physics, and we can also test that the relativity is valid in extreme conditions. So this seems to be just fundamental physics, but in fact, if we think about telecommunications and when we use our smartphone or the navigation on airplanes, there are corrections which are taken into account relativistic effects. So what we are studying now is connected to what is applied science. This is a list of the open questions that we have on cosmic ray science, the study of neutrino, search for gamma rays, trying to do physics beyond the standard model. So this is all related to astrophysics and cosmology, but you will see also regarding atmospheric science for the the way in which we would like to see this event. I was already mentioning that these events are extremely rare. For the Italians, they know the size of the Aosta Valley. So this is the experiment in Argentina. The largest one is comparable to the size of the Aosta Valley, one of the smallest regions in Italy. And if we would go to space from 2 events per month, we could hope to have 1 event per day. And the field of view of our experiment would be as big as Italy, or at least a huge portion of Italy. So this will be a huge leap in detecting these events. They look rare, but if we think every year there are millions of these ultra-energy cosmic rays that are falling on Earth. So if you are visionary and think into the future, we might be able in future generation to detect many, many more than what we are doing now. So what I like very much of our approach, which is this astronomical Earth observatory, is how it was called here in Japan. So for those who know kanji and they know how astronomical observatory is written, they would recognize the second, the third kanji, and the first one would be 10. So it would be 10 Mondai, 10 is the sky, but because our observatory is pointing to the Earth, 10 was substituted by Chi, which is the Earth. So it's an astronomical observatory which is pointing to the Earth and gives the opportunity also to detect many other atmospheric phenomena like lightning, meteors, air glow, and all what we can see looking at ground and do remote sensing. So again, this is a bit of history of all the missions that we have realized so far and the kind of science that we would like to do. And you see that there was really an involvement of the most important agencies, space agencies around the world, aside from all the institute and university which joined the project. We made a lot of advancement in different sectors, and you can see here also the countries which were most involved in that. So the optics, the photosensors, the detection unit, the electronics, the data acquisition, the data processing and control, up to the fabrication of assembled photo detection modules. So all our concepts have been evolved into technology that can be used also for other applications, as it was already mentioned by Wada Sensei before, and I will briefly mention at the end of my presentation as well. Regarding the balloon program, this is what we have achieved so far, demonstrating with artificial showers that we can detect them with our technology. What we would like to do is to see the real one with the next balloon mission, and our collaboration meeting this week here in Japan is mostly devoted to the next balloon project. And of course, we have seen also other interesting phenomena. JEM-EUSO, which is this mission on the International Space Station that is done with the main purpose to look at the atmospheric science. We have already obtained very nice results. The first UV maps from the sky, looking at the Earth since decades, and then the systematic observation of meteors. So we are also looking at the TLEs. These are ELVs, very peculiar phenomena that develop in the atmosphere, in the ionosphere. And with our technology, we can see features which are difficult to see with other type of instrumentation. All our technology and science was also subject of education, and we were proud to have Luca Parmitano, the Italian astronaut, that during his Beyond the mission, he was responsible to start the acquisition for the first time of JEM-EUSO, our detector, and also to report about it to our president Mattarella in one video calls they had at that time. And as it was already mentioned before by Wada Sensei, the JEM-EUSO detector and concept has become interesting also to the study of space debris. This is the paper that was already shown before. You know that the debris are a problem, and what we are interested in are the debris of 10 centimeter or even lower that are difficult to be tracked. We have some idea models, for instance, by ESA or NASA, how many they are in the atmosphere, but we don't know precisely, and would like to have missions that are capable to have a better knowledge and in principle later on to track, and with the laser system of ADA Sensei also to the orbit them. Regarding this collaboration, JEM-EUSO, Italy, Japan, and Space Debris Project, we have also a patent, an Italian patent, that was a joint effort of Torino University and RICAN, and now we have submitted it also to Europe and US. They are under review. So just to say that our technology then gives also the possibility to have a patent, and we have other projects in future. Right now we are in a project funded by ESA with Italian space companies, ICO and TIVAC International. We are in phase A, hoping in future to have this kind of detector on the ISS, and also we presented our development at the International Astronautical Congress last year in Milano. So our future goals of the JEM-EUSO program are progress with ultra-high energy cosmic ray detection, thanks to the POEMMA balloon with radio mission scheduled in 2027, continue exploiting the mini-EUSO data for multidisciplinary studies, and also target a CubeSat mission for space debris application. So this is the main project that is ahead of us. The launch is expected in 2027. So another balloon mission to increase further the technological level of our instrumentation, with the goal to observe both ultra-high energy cosmic rays with fluorescence technique, and also with the Cherenkov light, and hopefully, if we are lucky, also maybe a neutrino, if we are extremely lucky, but we should think positively. And we will this time also a new type of detector, which is a radio detector, to make our science case even stronger. And this is a engineering model of the debris detector that we would like to have in space, that you can recognize is the technology developed within the JEM-EUSO collaboration, the mini-EUSO detector. And that's all. I thank you very much for your attention.
Questions? Otherwise,